Welcome to this explainer. Have you ever actually stopped to wonder what exactly happens to a medical scan after it's taken? Well, today we're going on a really fascinating journey. We're going to track the life of a medical image, starting right from the moment a scanner captures the raw data, all the way through a highly complex, step-by-step computer vision pipeline. Ultimately, we'll see how that raw initial image transforms into a life-saving, AI-driven diagnostic prediction. It is a meticulous and, honestly, an incredibly vital process.
But before we look at how we build these systems, we really need to understand why they have to be built so rigorously. 96% to 13%. In a recent study, researchers took a highly praised, super sophisticated deep learning model called VGG16. Now, on clean, normal MRI data, it achieved an incredible 96% accuracy. But when the researchers introduced specific adversarial attacks, these are tiny, almost completely invisible mathematical alterations to the image pixels, the model's accuracy absolutely plummeted to a terrifying 13%. It literally completely failed.
And that brings us to the core question of our entire explainer. How do we build an AI that can actually handle the super high stakes of healthcare? Because in medicine, a wrong prediction isn't just a glitch, right? It's literally a matter of life and death. We absolutely cannot afford a model that gets confused by slight variations, or different scanners, or just basic image noise. We have to build an ironclad pipeline.
Okay, let's dive right into this. Think of this as the ultimate assembly line, or maybe a medical residency for our AI. First up, acquisition, then pre-processing, model selection, training and validation, and finally, clinical integration.
Step 1. Acquisition. Basically, gathering the raw material.
So this is where we actually capture the data, using modalities like CT scans, MRIs, and X-rays. Now, in the consumer world, you and I are totally used to JPEGs and PNGs. But in healthcare, we use DICOM, digital imaging and communications in medicine. And a DICOM file is incredibly complex. It's not just a flat picture, it's this robust file packed with critical clinical metadata. So it contains the image itself, for sure, but also the patient's age, the specific settings of the scanner, the physical dimensions of the pixels, even the slice thickness of an MRI. This metadata is truly the lifeblood of a hospital's imaging network.
But here is the absolute most important concept to grasp at this stage. To a computer, an X-ray is just a mathematical matrix of pixel values. When a human doctor looks at a scan, they instantly see a broken bone or a lung nodule. The machine, it sees absolutely none of that. It literally just sees a giant flat grid of numbers ranging from dark to light. So our entire pipeline is dedicated to teaching the computer how to find meaningful diagnostic patterns within that massive grid of numbers.
Which brings us to step 2. Pre-processing. Refining the material.
This is where we translate those raw matrices into a clean, standardized language that the machine can actually process and learn from. Before our AI model ever even sets eyes on the data, we have to clean it up. So we run the images through a few key pre-processing steps. First is noise reduction, where we apply mathematical tools like Gaussian filters to smooth out visual artifacts and scanner noise. Second is normalization. This is where we adjust the pixel intensity values to a common scale, usually between 0 and 1, just so the AI isn't completely thrown off by extreme contrasts. Third, we have image scaling, because deep learning models require fixed, specific dimensions to function properly. And fourth is data augmentation, which is a really clever trick we're going to expand on in just a minute. And this brilliantly illustrates the massive paradigm shift in medical imaging. I mean, old-school computer imaging was entirely rule-based and physics-driven. Engineers had to manually code edge detection algorithms and explicitly tell the computer exactly what shapes to look for. But next-gen vision? That relies on deep learning. It uses automated feature extraction. We don't actually tell the network what a tumor looks like anymore. We just give it the data, and it learns the underlying patterns entirely on its own. But to teach it those patterns, we do have to give it the answers first. And this requires expert human annotation, which, as you can imagine, is painstakingly difficult and super expensive. We can't just crowdsource this to anyone. We need highly trained radiologists. They perform image classification, basically telling the system if a whole scan is normal or abnormal. They do object detection, drawing bounding boxes to highlight roughly where an anomaly is. And the most intense by far is image segmentation. That's where experts literally trace the exact boundaries of a tumor, pixel by pixel with their mouse, all to teach the AI absolute precision.
Moving right along to step 3, model selection. Choosing the engine for our AI.
The field relies on a few architectural heavy hitters here. The absolute foundational backbone is the CNN, or convolutional neural network. CNNs are brilliant at scanning an image and extracting spatial hierarchies, so starting with really simple edges and textures and building all the way up to complex shapes like organs. We also use RNNs for looking at sequential 3D slices over time, GANs for generating synthetic data, and increasingly we're seeing transformers, which are fantastic at grasping the global, overall context of an image.
Now, what's really interesting about this slide is the UNet architecture. In the world of medical image segmentation, UNet is completely king. It's famous for, well, its literal U-shaped design. As data moves down the contracting encoder path, the model captures the broad context of the whole image. Then, as it moves back up the expanding decoder path, it creates incredibly precise localizations. It also uses what are called skip connections to combine those high-level details with fine-grained pixels. The result? Absolutely pixel-perfect diagnostic masks.
Let's move to step 4 and see how this all builds up into training and validation, basically practice and exams.
So the engine is built, right? Now it's time for the AI to study for its medical boards. To do this safely, we have to split our data up really carefully, a lot like a student preparing for a massive test. We use the bulk of our scans as training data. Think of this as the textbook the AI uses to learn features and patterns. Next is the validation data. This is the practice exam. We use it to tune the model's parameters and just make sure it isn't merely memorizing the textbook, which is a really dangerous flaw known as overfitting. Finally, we have the test data. This is the final board exam, utilizing scans the AI has absolutely never seen before, just to prove it actually understands the medicine.
But we often run into a massive roadblock here. Medical data is incredibly scarce. We don't always have thousands of examples of rare diseases just lying around. So how do we train a data-hungry AI? Pure ingenuity. We use data augmentation, where we mathematically rotate or flip existing scans so the AI literally perceives them as brand new examples. We also deploy GANs and diffusion models. These are AI systems that can literally synthesize entirely fake yet anatomically flawless, high-quality X-rays to artificially expand our dataset. It's a game changer for training our diagnostic model much more robustly. And that brings us to our final stage, Step 5, clinical integration, graduation. Finally, our model passes its tests and leaves the laboratory for the real world. But listen, an AI is completely useless if doctors can't actually easily access it. So, the model is integrated directly into a hospital's PACS, the Picture Archiving and Communication System. PACS is the massive central network where all hospital imaging is stored and routed. By plugging seamlessly into this PACS architecture, the AI acts as a computer-aided diagnosis, or CAD tool. It works silently in the background, automatically flagging issues and streamlining the radiologist's daily workflow without ever requiring them to open a separate piece of software.
And the results we're seeing in the real world today are honestly nothing short of spectacular. These integrated AI pipelines are actively detecting microscopic lung nodules on chest X-rays, catching lung cancer at its absolute earliest, most treatable stages. They're analyzing the incredibly subtle complexities of brain MRI scans to spot the early onset of Alzheimer's disease. They're even reviewing retinal photographs to identify diabetic retinopathy, intervening just in time to save patients from irreversible vision loss. It's amazing.
So the crucial point here is that while the technology is seemingly miraculous, a massive barrier still remains. We call it the black box problem. You see, a deep learning model might be 99% accurate at detecting a tumor, but its internal math is so staggeringly complex that it cannot explain to a human doctor how it reached that specific conclusion. If a human specialist makes a diagnosis, you can just ask them for their reasoning. Actually, you can't ask a convolutional neural network anything. And in high-stakes healthcare, that lack of transparency fundamentally undermines clinical trust.
Which really leaves us pondering the frontier of this incredible technology. Can we eventually build truly explainable AI, systems that not only give the right answer, but can actually show their work so doctors can fully trust them? Or will the black box remain the ultimate barrier to fully automated medicine? It's a fascinating challenge for the brilliant minds working in computer vision today. Thank you so much for joining me on this explainer, and I really hope you walk away with a much clearer picture of how medical AI actually comes to life.